Dear students, today we'll see the third part of DCET 2019 question paper. So let's start with the first question, question number 41. Design equation for series element of a constant low pass filter is. Okay. Now here, if you remember constant low pass filter, now for low pass filtering, we know that we have to connect inductor in series and a capacitor in parallel. So we were having two configurations. One was T type and another was pi type. So T type was like this. This was in series inductor, then a capacitor in parallel, again a series inductor. So this was your T type low pass filter, L by 2, L by 2, and this is C. Similarly, we can also have pi type low pass filter. So inductor here in series, and we can have a capacitor here and one more capacitor here. So this can be a pi type low pass filter where inductor in series, and this is C by 2 and this is C by 2. Okay. Now in both the circuits we can see that the series element is inductor. Now to have a expression for inductor, we have to start our derivation from taking characteristic impedance. So if you take the a characteristic impedance is given as, okay, Z naught is equal to under root Z1 to the power of 4 upon 4 plus Z1, Z2. Okay. So here Z1 will be the uh, impedance in the series arm and Z2 will be the impedance in the parallel arm. So Z1 will be given as J omega L and Z2 will be given as minus J omega C. Okay. Now in this case, Z1 into Z2, if you do, it will be J square minus 1. So all those values you can substitute in this equation, and you can also take omega, that is angular frequency, is equal to 2 pi into frequency. Okay. So after substituting all this, we can get an expression for inductor, that is series element inductor. L is equal to R naught by pi Fc, and C is equal to 1 upon pi R naught Fc. Okay. Now here you can see the inductor element is a series element, and this is what is asked in the question. Design equation for series element of a constant low pass filter. So the series element L is given as R naught upon pi Fc. So from this, option B will be the right answer. That is R naught upon pi Fc. So here you can see the option B, that is R naught upon pi Fc, is the right answer. Then we'll go to the next question. Question number 42. Equation for a characteristic impedance of a transmission line is what? So the options are Z naught is equal to under root y upon z, Z naught is equal to under root zy, Z naught is equal to under root z upon y, and Z naught is equal to z square y. Okay, so under root z square y. So out of these four options, which is the right answer? Okay. Now, if you go to see what is a characteristic impedance, then a characteristic impedance is defined as the impedance looking into an infinite length of line. So it is the impedance looking into an infinite length of line. Its unit is ohm, and in this infinite line, no reflection occurs. Therefore, there is no loss of power, and all power sent down the line is absorbed. Similarly, when a line is terminated in its characteristic impedance. So if you terminate a line in its characteristic impedance, same impedance, what is its a characteristic impedance? It is said to be correctly terminated, and it will also have no reflection, and there will be no power loss. Therefore, a characteristic impedance Z naught of a transmission line is given as Z naught is equal to under root Z upon Y, where Z is the impedance and Y is the admittance. And this, if you expand, you can also write this as Z is equal to R plus J omega L and Y is equal to G plus J omega C. So as a whole, we can see that Z is equal to, Z naught is equal to under root Z upon Y is the equation for characteristic impedance of a transmission line. So in this option C is the right answer. So here option C, Z naught is equal to under root Z upon Y. So here you can say option C is the right answer, which gives the ratio under root Z upon Y as the equation for a characteristic impedance of a transmission line. Then we'll go to the next question. In amplitude modulation, okay, so in amplitude modulation, amplitude of the carrier signal is varied in according with the amplitude of dash signal. Options are a carrier, option B is information, option C is signal higher than carrier, and option D is none of this. So here, if you remember about amplitude modulation, so here we will be having a information signal. We'll be having an information signal which we have to send from one point to another, and to do that we require a high frequency carrier. There will be a high frequency carrier, and when you superimpose this and when we take the process, that is the amplitude of the carrier is varied according to the information signal, then we will get something like this waveform at the output, which will be varying according to amplitude of the information signal. So this will be your carrier frequency, whose amplitude will vary according to the instantaneous value of information signal. So this is your AM wave. This is your amplitude modulated wave. This is carrier. This is carrier. And this is information signal. This is information or message or modulating signal, information signal. So here in amplitude modulation, the amplitude of carrier is varied according to the amplitude, that the instantaneous value of the information signal. So option B will be the right answer here. That is information signal. That is your message, or it is also called as modulating signal. So here you can see option B is the right answer. That is information. Then we'll go to question number 44. Base 16 refers to which number system? Now, when we studied in digital electronics, the various number systems, the number system which is given in binary, okay, so binary number system will have a base of 2, and in that we have only two numbers, two digits which can represent every number, that is 0 and 1. Okay, after binary, we studied what was octal. In octal, we had 8 numbers of base of 8, and in that we had numbers as 0, 1, 2, 3, 4, 5, 6, and 7. So totally 8 numbers. Then comes the decimal number system, which we use in our daily life, whose base is 10. So there are numbers from 0 to 9. So these are your 10 numbers. So the base is 10. And then comes the hexadecimal numbering. So in hexadecimal number system, the base is 16. The base is 16, in which you can have numbers from 0 to 9, and then we can have numbers from A to F. So totally we have 16 numbers. 16 numbers. So it is to the base 16. So the base 16 refer to which number system? It is hexadecimal. So here option B will be the right answer. That is hexadecimal. So here you can see option B is the right answer. Then we'll go to the next question, question number 45. Which of the examples below express a commutative law of multiplication? Okay. Now here, if we remember a commutative law, whether in mathematics or in digital electronics, it is either for addition or for multiplication. And it says that if you are using addition, then we can say that say a plus b is equal to b plus a, and if it is multiplication, we can say that ab is equal to ba. So here what you are doing is, from these laws, it follows that any finite sum or product is unaltered. It is not changed by reordering its terms or factors. So in the first case, we saw that the left hand side is a plus b and the right hand side is b plus a. So if you change the order, the meaning, the sum of it will not change. Similarly, in the second case, if you see a into b is equal to b into a, so if you change the order of a and b, the product value is not going to change. Now, in this question, it has been asked that which of the examples below expresses the commutative law of multiplication. So we want multiplication. So if you see these options, their option D will be the right answer, which is saying that C multiplied by D is equal to D multiplied by C. So option D will be the right answer here, which gives our commutative law of multiplication. So here you can see option D is the right answer here. Then we'll go to the next question. Applying the De Morgan's theorem to the expression shown x plus y whole bar plus z bar the whole bar, we get. Now to this equation, we have to apply De Morgan's theorem. Now De Morgan's theorem says that complement of the product of all terms is equal to the sum of the complement of each term. That means complement of the product of all terms if you take. Now here we'll take an example and show you. So here you can see A into B into C. So this is completely barred. So it is complement of product will be equal to sum of the individual complements. So A bar plus B bar plus C bar. Similarly, we can have complement of the sum of all the terms is equal to the product of complement of each term. That is, if you have A plus B plus C, this complete bar is equal to A bar multiplied by B bar multiplied by C bar. Okay. Now these are your De Morgan's theorem statements, and based on this we have to solve the above equation. So the above equation is given as sum. So you can have sum of x plus y, this is one term, plus z bar, this is another term, the whole bar. Okay, now this is the sum of two terms, and if you open up this according to the De Morgan's theorem, what will come is x plus y bar and one more bar. Okay, now this will be multiplied by z, and this z also will be having its original bar and the bar of the De Morgan's theorem. Now this, if you see bar and bar, they will cancel out each other, so it will be nothing but x plus y multiplied by z. X plus y multiplied by z. Now this answer, that is x plus y multiplied by z, is the option A answer. So option A is the answer for the expression. So applying the De Morgan's theorem to the expression given, we get the answer as option A, x plus y into z. So here you can see option A is the right answer here, x plus y into z. Okay. Then we'll go to the next question. The ones complement of 101010 is. Now if you take this number 101010, so 101010. So if you take ones complement, you have to invert every individual bits. So this one will become 0, this 0 will become 1, this 1 will become 0, this 0 will become 1, this 1 will become 0, and this 0 will become 1. So it is 010101 to the base 2. Okay, so that is the binary number. So in these options, you can see that option B is the right answer. 010101 to the base 2. It is the ones complement of 101010 base 2. So here you can see option B is the right answer. Then we'll go to the next question, question of 48. A single bit full adder. Okay, a single bit full adder adds. Options are two 2-bit binary numbers, two 4-bit binary numbers, two single bit and one a carry bit, two 2-bit numbers and one carry bit. Okay. Now here, if you remember a full adder truth table, Then we know that there were three inputs what we used to add. Okay, and those three inputs what we took were, say, input one is A, input two is B, and the third input will be the carry input. So these are the inputs what we took, and then the outputs what we got was sum and carry out. Okay, now these three inputs, say for the example, the inputs are 0, 0, 0. The sum will be 0, carry out will be 0. If the inputs are 0, 0, 1, the sum will be 1, carry out will be 0. If the inputs are 0, 1, 0, the sum will be 1, or carry out will be 0. In this way, we are going to have all the three combinations. So it will be 2 raised to 3, that is, we'll be having around 8 combinations of the inputs what we can give. But the question asked here is, what actually we are going to add? A single bit full adder adds what? So here we can see it is going to add one bit, second bit, and a carry bit. Okay, so two single bits and one carry bit. That means option C is the right answer here. Two single bit and one carry bit is what the full adder is going to add. So option C is the right answer here. Two single bit and one carry bit. Then we'll go to the next question. Question of 49. The edge triggered flip-flops respond to the inputs present at a transition of the clock pulse, when clock is high, when clock is low, when clock signal is not given. Now, when we speak about edge triggered, then we can take a reference of a clock pulse. This is a clock pulse. Now, when a clock pulse is been going to use as edge triggered, if the edges are going to trigger the flip-flop, then we'll be having two edges. This is the leading edge and this is the falling edge. Okay, so leading edge and falling edge. So here, this is nothing but you're going from low state to a high state, and this is nothing but you're going from high state to low state. Okay, that means you're going to transit. You're having a transition in the clock level either at the leading edge or at the falling edge. That means the option A, that is transition of the clock pulse, is the correct answer. So the edge triggered flip-flop respond to inputs present at transition of the clock pulse. That is, it is going to respond for the edges of the clock pulse. That it is going to respond for the leading edge or the falling edge of the clock pulse. And that is nothing but transition of the clock pulse. So option A is the right answer here, or transition of the clock pulse. Then we'll go to the next question. Find the resolution of a 4-bit DAC, that is digital to analog, a converter system, if the full scale output voltage is 15 volt. Now here, a resolution of a DAC, if you see the definition, it is the smallest change in the analog voltage it can detect. It is the smallest change in the analog voltage it can detect, which is also known as step size of DAC. Now, for a n-bit DAC, okay, for a n-bit, this is a general formula for n-bit DAC. Okay, the resolution formula is resolution is equal to range range upon 2 raised to n, where n is the number of bits minus 1. Okay. Now, if you see the above question, find the resolution of a 4-bit DAC. 4-bit DAC means n is equal to 4. If the full scale output voltage is 15 volt, that means range is equal to 15 volt. If you substitute these values in the above formula, we get a resolution is equal to 15 upon 2 raised to 4 minus 1. Okay, this is nothing but 15 upon 16 minus 1. This is nothing but 15 upon 15, which is nothing but 1 volt. 1 volt. So here, the resolution of 4-bit DAC system, if the full scale output voltage is 15 volt, is 1 volt. So option B is the right answer here, 1 volt. So here you can see option B, 1 volt is the right answer. Then we'll go to the next question. Which of the following memory is volatile? Okay. Now, when we have studied memories in digital electronics, we know that volatile memory is one that requires power, that requires power to maintain the stored information. It retains its contents while the power is on. But when the power is interrupted or if the power is lost, the stored data is quickly lost. And this happens in memory, which is called as random access memory, that is RAM. So RAM, that is random access memory, RAM, is a volatile memory. That is, it will lose its content. The stored data will be lost when the power is interrupted. So here you can see option C, RAM is the right answer. RAM is a volatile memory. Then we'll go to the next question. Aliasing effect occurs if dash, that is where Fs is the sampling rate and Fx is the highest frequency component. Now we know that according to the sampling theorem, okay, according to the sampling theorem, the sampling frequency Fs should be greater than or equal to the highest modulating frequency, twice the highest modulating frequency, that is 2fx, so that we can reconstruct the original signal back from its samples. That is what we studied in sampling theory. Now, if this condition, which is a Nyquist condition, which is given as fs is equal to 2fx, if this condition is not followed, and if you take a condition where sampling frequency is less than to fx, then in the spectrum we can see that the terms overlap each other, and in that overlapping, the highest frequency identity of the information will take the lower frequency identity of the next double side band. That is what we have studied, and that effect of overlapping the spectrum, that effect is called as aliasing effect, and it happens when we are not maintaining the sampling frequency either equal to or greater than twice the highest modulating frequency. So if Fs is less than 2Fs, then it is going to give aliasing effect. So here aliasing effect is occurred when your option A is there, that is the sampling frequency Fs is less than twice the highest modulating frequency. Then in that case we'll get that uh, will get that effect which is called as aliasing effect, where the recovery of the information signal at the end will not be proper, and the terms where the spectrum, the frequencies will get overlapped on each other. So it is called as aliasing effect. So fs is less than 2fx, this condition will give aliasing effect. Then we'll go to the next question, question of 53. Sequence to generate PCM, that is pulse code modulation signal. Now, in pulse code modulation signal, what we do is we'll be having a analog signal. That analog signal will be converted into samples. It will be converted into samples. Then it will be quantized to a specific values levels. It will be quantized, and then every level will be encoded and given a binary sequence, that is data. Okay, so it is analog signal, then sampling, sampler, then you have a quantizer, then encoding. So the sequence in these four options, option D will be the right thing, where you have first the analog signal. This will be the analog signal. Then you will be having samples of that analog signal. You can see the samples of analog signal. Then every sample will be compared with a level. So it will be given a standard level. And then that standard level will be given a encoded value in binary. And hence we convert analog to digital signal. So this is the process, that is the analog signal, sampler, quantizer, and encoder, which the PCM follows. So option D is the right answer here. Here you can see option D, that is analog signal, sampler, quantizer, and encoder is the right answer. Then we'll go to the next question, question number 54. Slope overload distortion and granular noise type of distortion are found in. So that we see when our signal is having a steep slope, and then say at some time it is not varying at all. If you use a linear modulation to overlap it, okay, so here you can see You can have linear modulation like this, where the step sizes are same. If you are having constant step sizes, then when the analog signal, say this is your analog signal, then the step size which was hunting the analog signal, this is the which was hunting the analog signal, that will not reach to the analog signal till some point when the analog signal was steep, and this will be the error which will be called as slope overload distortion. And when the analog signal is not varying, then in that case also the step sizes become large for it, and there comes a error which is called as granular noise. Now both these errors are seen in delta modulation. They are seen in delta modulation. And if you want to eliminate this error, then the step sizes should be varied, and we have to go to the next method, that is adaptive delta modulation. Okay. Now these are the two errors, that is slope overload distortion and granular noise are the two distortions which are found in delta modulation. So option C will be the right answer, that is delta modulation. So here you can see option C, delta modulation is the right answer. Next, we'll go to see question number 55. In dash format, the a transmitted pulse waveform occupies the full duration of a symbol. Now, if you're having a full duration of a symbol, say this is a duration of a symbol, one duration, second duration, third duration, fourth duration. Okay, so this will be a first duration, second duration, third duration, and fourth duration. Now, if you want to represent logic 1, you can represent 1 as like this, 0 as like this, 1 as like this, 0 as like this. So this is 1, 0, 1, 0. This is from 0 to V volt. We can also represent ones and zeros from 0 to V volt as 1, 0, 1, 0. Okay, now this is your 1, this is 0, this is 1, this is 0. So this is from 0 to V, and this is your minus V. Okay, now the top one is called as unipolar NRZ, and the down one is called as polar NRZ. Now, what is NRZ is non-return to zero. That is the complete duration, the complete width is used to represent the symbol. It is not halfway coming to the zero line. So the complete width is used to represent the symbol, either it is 1 or 0. So the format in a transmitted pulse waveform occupies the full duration of a symbol is non-return to zero, that is NRZ. So option B is the right answer here. NRZ is the right answer. Then we'll go to the next question, question number 56. Dash involves switching the frequency of a sinusoidal carrier between two frequencies in according with the incoming binary data while keeping the amplitude and phase constant. Now say if your incoming binary data is 1, 0, 1, 0. Okay. So this is your incoming binary data. Now, if there are two frequencies, one frequency for logic 1 and for logic 0, I'm frequency for logic 1, logic 0, logic 1. Okay, so here you can have frequency F1, F2, again you can have F1, F2, again you can have F1. So you are going to switch between two frequencies, and this method in which it is having switching of the frequency of a sinusoidal carrier between two values in according with the incoming binary data. This scheme, this modulation system is called as binary frequency shift keying. So it is option A, which is the right answer here, which is binary FSK. BFSK is the right answer. So here you can see option A, BFSK is the answer for this definition. Then we'll go to the next question, question number 57. In dash, multiple signals share the common bandwidth of a single communication channel, each occupying a separate position of the bandwidth. Now, this is possible because of modulation, and in a given bandwidth of frequency, a part of it can be each part of it can be given to a individual channel. So here, if you see, if you are having a bandwidth of say 0 to 100 kilohertz, 0 to 100 kilohertz, then you can have 0 to 10 kilohertz one channel, 10 to or 20 kilohertz another channel, 20 to 30 kilohertz another channel, or 30 to 40 will be another channel. In that way, you can allocate different bands for different channels, and this system is nothing but your frequency division multiplexing. The signals are placed on the basis of frequency. Okay, so FDM is the right answer here. Option D, that is FDM, frequency division multiplexing. So here you can see FDM is the right answer. Then we can go to the next question. Unguided media use dash as the transmission medium. So in unguided media, you don't have any physical wire or cable or fiber between the transmitter and receiver. So it is going to use air. It is going to use air. It is a wireless communication. It is going to use air as the transmission medium. So here option C will be the right answer. Unguided media use air as the transmission medium. So here you can see option C, that is air, will be the right answer. Then we'll go to question number 59. Dash are used when spanning distance is less than 2 or 3 kilometers in connection with computer networks. So if you're having a computer network and whose area covered by that network, a geographical area covered by that network is around 2 or 3 kilometers, then it comes under the category of local area network, that is LANs. So option A will be the right answer here, LANs, that is local area networks. So here you can see option A is the right answer. Then we'll go to question number 60. Dash layer in the OSI model. So in OSI model, there are 7 layers. Dash layer is responsible for assigning a globally unique address to every device. Okay. Now we know that the first layer will be the physical layer where you will be having the signaling method and the data will be in a 0, 1 form. And then we'll be having a data link layer, and then the third will be on network layer. A network layer is one where we are going to assign a unique address to every device. So here in this case, dash layer is in the OSI model is responsible for assigning a globally unique address to every device's network layer. So option B will be the right answer, that is network layer. So here you can see network layer in the OSI model is responsible for assigning a globally unique address to every device. Okay. Thank you, students.